At the turn of the century, a French meteorologist, Léon Tesseranc-de-Boer, announced a startling discovery. Between 30,000 and 60,000 feet, the temperature stopped growing colder with altitude and even began to rise. With his sounding balloons, de Boer had discovered a zone which we now call the stratosphere.
Don't go up in that big balloon, Dad. Go back to the pier saloon.
70 years later, the stratosphere is still remote, visited only by space-bound astronauts and pilots of special aircraft. But today the stratosphere is coming under increasing scrutiny, for it is a vast reservoir that can trap natural chemical substances and man-made pollutants. In the lower atmosphere, the tiny particles, called aerosols, are washed out in a few days. But the stratosphere lies above the world's weather and has no cleansing process. Contaminants can stay for months or even years and spread over the globe from their original sources. In concentration, aerosols scatter the sun's rays to produce brilliant twilight colors. The explosion of Krakatoa in 1883 caused spectacular sunsets around the world for months afterward. In recent years, astronauts have described aerosol layers lingering high over the Earth. Air Force balloon photos revealed 4 such layers. Today, using a variety of techniques, atmospheric scientists are endeavoring to learn more about the nature of the stratosphere and its constituents.
Okay. You got that one. Let's try for another.
Changes in the thickness and concentration of the aerosol layers can be measured precisely through LIDAR soundings. Laser beams fired into the night sky are reflected by the layers, and their echo is monitored at a ground station.
Okay, that's looking pretty good. We're getting out to about 45 kilometers. I think I'm going to record it.
Did we get anything out at 20 kilometers?
Well, I'll have to... No, it's relatively clear.
But to find out what the aerosols are, where they come from, and how they distribute themselves globally, we need samples from the stratosphere itself. In 1971, chemists from the National Center for Atmospheric Research began cooperating with the Air Force and the Atomic Energy Commission in a series of high-altitude aircraft and balloon flights to collect aerosol samples. The 58th Weather Reconnaissance Squadron flew missions from 4 bases along paths stretching from northern Canada to southern Argentina. Round trips were made at altitudes from 40,000 to 63,000 feet to give the chemists data throughout the Western Hemisphere. In addition, balloon flights over Alaska, Texas, Panama, and Australia provided data on the vertical distribution of chemicals to heights of 70, 80, and 90,000 feet. One series of flights started from Kirtland Air Force Base in New Mexico. The RB-57F, a military aircraft with modified wings, is especially suited for flight in the thin air of the stratosphere. For sampling purposes, a tubular airfoil was fitted beneath the plane, and filter racks were installed in the bomb bay. Special filters capable of trapping particles as small as 1/millionth of an inch in diameter had been prepared earlier at NCAR. After a meticulous washing to remove any residual contaminants, the filters are taken to a clean room for mounting in holders. Cleanliness of the filters is critical, since the concentration of particles in the stratosphere is extremely low. At Kirtland, clean filters are loaded into their rack aboard the aircraft. When the plane reaches its designated altitude, each filter will be lowered sequentially into the airfoil, much like a record in a jukebox. After a 30-minute exposure to a stream of stratospheric air, it is withdrawn and replaced by the next filter. A self-powered unit for measuring ozone and water vapor is also included on sampling missions. Since ozone concentrations are directly related to the physical structure of the stratosphere, this data will be instrumental in explaining the distribution of aerosols. Plastic tubes connect the ozone and humidity sensors to external air sampling ducts.
Another 10 miles, we'll be changing to number 3 filter. That goes in at 57 north. And it's 40 plus 20 seconds now. And we have 44.7. 110 on the heading. 176 on the airspeed, minus 27.8.
Northwest 362, anchor center, roger.
Okay. Opening the door. Paper number 3 is in.
Dog 89, report Pleasant intersection. Okay, report Pleasant, and you're clear to the Howard intersection. Bold west, and expect further clearance at 1955, but...
Back in the laboratory, each filter is cut into sections and prepared for analysis.
He gets quadrant number 1. And quadrant number 3. Here's Al's.
Okay, that's quadrant number 1.
Right.
Okay.
And we'll take quadrants number 2 and 4. I'll roll this up tight this time. Okay, I need our vial, Julian.
Okay.
Put
Foxtrot
this
6.
in. Foxtrot 6.
Release release that air.
Yeah, that air.
Through a technique called neutron activation, chemical constituents returned from the stratosphere can be identified and measured. The filter sample is transmitted to a shielded chamber where it is bombarded with atomic particles.
Neutrons are on.
Okay, probably 170 kilovolts to the 3 milliamp.
We're at 100 at 2 mils. Okay, she's up to full power at 170 and 3.3. Okay, 5, 4, 3, 2, 1. Neutrons off.
After neutron bombardments, the sample is removed and placed in a counting chamber. Each element that captures a neutron emits a distinct kind of radiation, which is a key to its identity. The sample itself remains intact. It can be checked for reference levels of other chemicals at any future date. In another laboratory, stratospheric constituents are extracted from the filters for analysis. Reagent solutions flow together automatically and convert the samples to colored liquids. The extent of coloring is measured by a light beam, and the amounts traced graphically. The chemicals are measured to concentrations of less than 1 part per million. The results begin to yield a picture of the distribution of stratospheric constituents. Ozone readings recorded during flights over a 4-day period provide a background map of the stratosphere against which the other constituents are compared. These readings are for the northern latitudes only.
This chart shows the distribution of ozone that was measured in the stratosphere early in June of 1971. The measurements extend from 25 degrees north latitude up to 75 degrees north latitude, and they're made at 40, 45, 50, 55, and 63,000 feet. Now, the ozone is produced at higher elevations than these, and you would expect mixing to move the ozone northward and spread it downward, and therefore you'd expect the concentrations of the ozone to decrease through the stratosphere as you approach the tropopause, and that's what you observe here. Also, one would expect to find the ozone concentrations higher northward or poleward of the jets. In this case, there's a jet stream located here, another jet here, and you'll notice there are low concentrations south of the jet, higher concentrations north of the jet. The other thing that has to be considered is that it takes approximately 4 days for these measurements to be made, and therefore we have to make a meteorological analysis for each particular day before we can properly interpret the data.
Positive correlations were found at lower altitudes between amounts of ozone and radioactivity. But at the highest level, the two were negatively correlated. Most radioactive particles are injected directly into the lower stratosphere by nuclear testing. French tests during the summer of 1971 caused a great increase of radioactive particles in the filters returned from September flights. By tabulating the distribution of other constituents, atmospheric scientists can begin to deduce something about the processes which occur in the stratosphere.
One of the interesting observations that we see in all this data is that the constituents have similar types of distribution. And this is in spite of the fact that they've all have different sources and undergo different types of chemistry in the stratosphere. For example, the nitric acid vapor is formed at higher altitudes and diffuses down to these levels. The sulfate starts out as a gas, sulfur dioxide, in the troposphere, and in some way penetrates into the stratosphere and is oxidized there to particles. Calcium and magnesium, on the other hand, also start in the troposphere, but they have to enter the stratosphere as particles. And in spite of all these differences, we see that they have a similar distribution of concentrations. The explanation for this is that the distribution is controlled primarily by the air circulation in the stratosphere, rather than by the particular source or the type of chemistry each constituent has undergone.
One surprise was an unexpectedly high level of bromine relative to its sister element chlorine.
The bromine that we are measuring in these stratospheric samples could likely come from three different sources. Pollution products from gasoline additives, of course, has been measured quite extensively in cities. The second source could be volcanoes that inject material directly into the stratosphere. And the third source that we should consider, I think, would be sea salts that originate from the oceans. As to the volcanic possibility, we are currently analyzing some volcanic fume material for bromine and chlorine to see if that could account for the stratospheric measurements. The most interesting possibility would be sea salt. Because the concentration of bromine relative to chlorine in the stratospheric material is pretty high, if sea salt is responsible, we'd have to have a very significant chemical enrichment of bromine to account for the bromine in the stratosphere.
The data from these sampling missions has also shed light on a phenomenon which has intrigued atmospheric scientists since its discovery by Christian Junge in the late 1950s. A sulfate layer in the lower portion of the stratosphere. 2 to 3 miles thick, this layer was once thought to come from sulfur gases emitted by bacterial action in the oceans. Vaporized meteors, volcanoes, and man-made pollutants were also suspected sources. In the mid-60s, measurements showed a large increase in sulfate concentrations, but by 1970, the level seemed to have dropped again. Could man somehow be responsible? Or if not, what could cause such dramatic fluctuations?
The concentrations of the stratospheric sulfate are similar in both hemispheres. This is really interesting because exchange of air between hemispheres is limited, and therefore crossover of these trace constituents between hemispheres is limited. One would guess that if a material was formed at the surface in the northern hemisphere, predominantly such as air pollution, that its concentrations would tend to be higher in the northern hemisphere. The fact that we see the southern hemisphere sulfate concentrations as high as those in the northern hemisphere suggests that air pollution at this time is not a primary contributor to the stratospheric sulfate aerosol layer.
The evidence leads to volcanoes as the primary source of stratospheric sulfates. Most likely, the great increase during the 60s was related to the eruption of the South Pacific volcano Agung in 1963. As our knowledge of chemicals in the stratosphere grows, new questions are posed for the next series of flights. Until now, man's impact on the stratosphere has been limited. But what will be the effect of uncontrolled industrialization, or exhaust from supersonic transports, or some unsuspected source of pollution? There are yet no certain answers, but these sampling missions will provide us with baseline measurements by which to judge our impact in the future.